I think it is the right time to have our very last talk of this conference. Tutorial from David Cortie. Okay, so I'll briefly introduce him. David Cortie obtained his PhD in physics from the University of Wollongong in 2013 and went on to postdoctoral work at the University of British Columbia, the Max Planck Society, the Australian National University, and the Australian Nuclear Science and Technology Organization. In 2017, he was awarded an Australian Research Council Discovery Early Career Research Fellowship. He is also an associate investigator with the ARC Center for Future Low Energy Electronics Technologies. And in 2021, David joined the Australian Nuclear Science and Technology Organization as a neutron scientist specializing in the applications of neutron scattering to characterize magnetic and thermoelectric materials, exploring the link between quantum phenomena and functionality. And now, David, the floor is yours.
Well, thank you very much for that introduction. Can you hear me?
Yeah.
Great. So I'd first like to start by thanking everyone in the organizing committee. Since I'm the last speaker, it falls to me to say how excellent this event has been. It's definitely one of the best virtual conferences I've been to. So congratulations on the great scope of talks and how smoothly everything's run. So as mentioned, yes, I'm from the Australian Nuclear Science and Technology Organization. So we're on the east coast of Australia. We're about 40 kilometers south of Sydney. And this is a very beautiful part of the coastline. You can see there's the Royal National Park full of trees and wildlife, and we're sort of just on the edge of that. And ANSTO administrates and runs the only nuclear reactor in Australia, which is a research reactor called Opal. Now, at the moment, actually, we're locked down because of COVID-19, so I'm not at ANSTO. I'm a little bit further south in my hometown of Wollongong, and coming to you from this beautiful part of the coast there. And I should say, you know, this entire coastland traditionally is the land of the Darawal people and the Gadigal people of the Eora Nation, and actually they were meeting here for thousands of years to discuss science. So in a way, what we're doing today is a continuation of a great tradition, and I'd like to acknowledge their elders past and present. So ANSTO, as mentioned, runs this nuclear reactor. It's the Opal light water reactor. This is a photo down into the fission core. And this is an actual photo, no special effects. That blue color that you see is the Cherenkov radiation from particles and charged particles that are faster than light speeding down in the water, which acts as a radiation shield. And this is a multi-purpose reactor. So one of the main functionalities it does is develop medical isotopes that are shipped all across Asia and into many parts of the world. There's also science looking at neutron activation and ways to modify materials with neutrons. And there's a big commercial operation looking at silicon transmutation doping for electronics applications. And finally, there's the part of ANSTO that I'm involved in, which is really doing scientific research on materials and physics and chemistry and biology using neutron beams. So my area of passion is looking at condensed matter physics. I'm a physicist by training, and most of the research I do today is part of a big consortium across Australia that's looking at new types of materials, topological materials, atomically thin materials. And this is part of a center called the Future Low Energy Electronics Technology Center. And it actually involves many different universities and ANSTO, and some international partners as well, like in New Zealand, McDermott, and also some labs in the US and China. So this is a big international collaboration, and I'd just like to explain sort of why we're interested in finding a solution for low energy electronics. So you may have seen this graph that appeared in Nature a few years ago, and it projects the electricity usage across society, and things are growing exponentially, right? And there's this projection by 2030 that information technology will consume around 20% of the overall electricity usage in society, which is obviously very high and a big barrier towards a sustainable society. And when we look at these areas of growth, it's interesting. You can see the blue areas grown and the green areas are really where the major growth is. So these are the data centers and the networking, okay? Whereas individual devices such as your phone or computer are actually staying the same or shrinking. And this giant growth reflects the movement towards cloud computing, big data, and other things where more and more of the computation and data is being stored somewhere in a big server. So we no longer see that electricity usage personally in our devices, but we're still paying for it as a society. And so we need some technology that will reduce this exponential growth. And there are many different competing ideas that are being explored across different universities in Australia. My particular interest is the idea of energy efficient topological spintronics. Can we create a topological transistor that performs better than current transistors? And along the way, there's this idea that ultra-thin magnets can play an important role. So today, I'm really going to focus on the discussion on the physics and the applications and challenges of ultra-thin magnets. And then I'm going to talk about this technique that we have at ANSTO called Polarized Neutron Reflectometry to study these. And finally, I'm going to just touch on how we can use density functional theory to calculate properties of thin magnetic slabs and also support reflectometry experiments. So physics of ultra-thin magnets actually is quite old. I mean, there's been discussion about, how two-dimensional magnets are a new thing, but in some sense, ultra-thin magnets have been around for a long time, and they're very important in today's technology, right? So, tunneling magnetoresistance devices in your hard disk, you're probably using one of these right now. There's also heat-assisted magnetic recording coming on the market this year. And these all involve very, very thin layers. And for example, this is an example of a TMR stack. You'll have a cobalt iron alloy that is less than a nanometer thick in certain layers of the magnetoresistance sensor. And when we think about how many atoms that involves, for an alloy, it's not many. So it's still a three-dimensional object, but this is a unit cell of cobalt iron, one of the phases anyway, and it's just a few atomic layers thick. So it is almost at the two-dimensional limit. And the question, I suppose, is in wanting to shrink devices further and make them more energy efficient, there could be an advantage towards going towards even more two-dimensional magnets. But there's always been this belief, perhaps, that this would be self-defeating. And that's largely because of this famous theorem that was published in the 60s by Merman and Wagner. And actually, our previous speaker just discussed this, and I think he did a good job of this idea that, Merman and Wagner put forward that ferromagnetism or anti-ferromagnetism are actually impossible in one or two-dimensional magnets, provided those magnets are described by Heisenberg exchange interactions. And so many, many people for a long time felt that two-dimensional magnets were sort of forbidden, but we should really look at the fine wording of what Merman and Wagner were saying. They were saying this applies to two-dimensional isotropic spin Heisenberg models with finite range exchange. And that's not every type of magnet, but at the time that they were writing this paper, many people felt this captured the vast majority of magnets. But we now know that this is actually not the case. And so, as our previous speaker mentioned, in the past few years, people have really started to find a whole new generation of two-dimensional magnets that are only a single atomic layer thin, chromium iodide, iron germanium telluride. We've had a few excellent talks about that during these conferences, this conference. And of course, these show that two-dimensional magnetism is possible. But I should say, this is really just the latest implementation of two-dimensional magnetism. The history of two-dimensional magnetism has a very long history, and it starts in 1944 when Sager showed that the two-dimensional Ising magnet has a critical phase transition. And this was a mathematical proof, but it laid the groundwork as early as the 40s for the existence of two-dimensional ultra-thin magnets. And already very important experiments with neutron scattering in the 60s found examples of two-dimensional magnets which were formed in three-dimensional crystals where you had two-dimensional planes that were decoupled from each other because of frustrated interactions or because they were very far from each other. And so these were quasi-two-dimensional systems that were already known in the 60s. And by the 70s and 80s, people had mastered and growing monolayer thick transition metal films. So the first ARPES showing exchange splitting in cobalt, for example, was in 82 in a monolayer cobalt. So two-dimensional magnetism has a long history, but what's really exciting about this new generation of ultra-thin magnets, I think, like graphene, they can be exfoliated using very simple methods. And also they combine very heavy elements like germanium, tellurium. So many of them have non-trivial topology in their electronic band structure. But you may still be wondering, well, what is it that allows these two-dimensional magnets to exist? Given that, in 66, Merman and Wagner said two-dimensional magnets were forbidden, how are these things actually working in practice? And I think to explain this, we should understand the difference between the Heisenberg and the Ising model, right? So in the Heisenberg model, I can picture that I have a lattice, and on each of these lattices, I have a magnetic spin. And these magnetic spins are coupled to each other through some exchange interaction that wants them to align either parallel or anti-parallel, depending on the sign of J. So here, if J is positive, this would be the lower energy state would be parallel. But in the Heisenberg model, these spins have a continuous symmetry. They can rotate like a classical vector to point along any direction, okay? And this is what Merman and Wagner were talking about in the isotropic Heisenberg model. They showed that such a magnet would never undergo a phase transition into a true long-range ordered state. It may enter into exotic kind of long, short-range ordered state known as the Kosterlitz-Thule state, but it would never become a true ferromagnet, okay? But importantly, if you take another example or simplified description of the same magnet here in the Ising formalism, all right, we now replace these spin variables with discrete integers, which are the spin direction. And basically what we're saying is, again, we have spins on the lattice, but here the spins can only point along one axis, say the Z direction, okay? So they're constrained and they only have 1 degree of freedom. And this is the solution that Ansaga showed did exhibit two-dimensional magnetism, and he showed that as early as 1944. Now, importantly, the real magnets that we deal with practically are somewhere between these two limits, and they're neither perfectly Heisenberg nor perfectly Ising, but usually we take account of this spectrum of properties by adding a uniaxial or some other form of anisotropy to the Hamiltonian in this form. And that is already enough. Even if this is very small, it can be enough to induce critical phase transition. Indeed, Banda and Mills already showed in 1988 that an arbitrary small anisotropy will lead to a two-dimensional phase transition. So the existence of two-dimensional magnetism is well established. It has a long history going back. But what's really exciting about these new magnets, of course, is that they combine these heavy elements. They combine topological physics. And this is quite new. It's really only popped up in the last 15 years in condensed matter. And the idea, of course, is that if we look at the electronic band structure, magnetism acts like a Zeeman splitting term and splits off certain bands in energy, okay? But if we then add a spin-orbit interaction term, it becomes a lot more complicated because the spin-orbit interaction term behaves like a K-dependent magnetic field, and it intermingles these bands, which can lead to a variety of fascinating electronic effects. And we've had lots of talks about that during this conference as well. I'll just give probably the most famous example of the kind of effect that's being studied today, and that is, this quantum anomalous Hall effect. So if you take a topological insulator with ferromagnetism, out-of-plane ferromagnetism, it breaks time reversal symmetry and introduces this very novel electronic state that was predicted in the 80s, but only finally achieved in 2010. And this novel electronic state is characterized by having a quantized Hall resistance and a vanishing longitudinal resistance. Okay, so it basically is like the quantum Hall state. You have electrons moving around the edges of the samples. They're dissipationless. They cannot be scattered because of this unique spin texture. And this makes them very, very energy efficient. So it's a very exciting discovery. And in a way, it's kind of a little bit like superconductivity, except it's an entirely different physical mechanism. And there's this idea that perhaps it could be scaled up to many hundreds of Kelvin. Currently, though, the best realizations are still just down at a few Kelvin operational temperature. So there are other examples of interesting topological effects that also occur in ultra-thin films. Of course, there's also the quantum spin Hall effect, the Nernst effect, anomalous thermal Hall effects. There's been magnetic exchange bias, Kondo effects. So there's really a jungle of interesting physics in these new magnetic phases that have come along. Okay, so the classic way, and what's really exciting, and we just actually heard a talk about this very thing, is of course the classic way to rapidly prototype a device is in these van der Waals two-dimensional magnets is to use basically Scotch tape and place a small crystal onto a substrate. Usually this is stamped onto silicon dioxide. Sometimes thermal release tape is used to help the process, and then sputter some contacts to do anomalous Hall measurements. And this is the main way, of course, to measure the magnetic state of a sample. And of course, this is the Hall resistance expression. We have one term which is linear in the applied magnetic field, but we have another term in a magnetic system which depends on the magnetization of this ultra-thin layer. And so people are constructing these beautiful devices with 1 or 2 or 3 atomic layers and doing anomalous Hall measurements systems. And this is the main source of information about the magnetization of these ultra-thin phases. And I think this is wonderful because it is really close to spintronic functionality right from the beginning. The only caveat here is that, Unfortunately, in these topological phases, well, fortunately or unfortunately, you can make your own decision. But the fact is, this simple proportionality that applies here between the magnetization and the anomalous Hall resistance, that certainly applies in a simple ferromagnet. But in a topological magnet, the anomalous Hall contribution has three contributions, one of which comes from the Berry phase, or the intrinsic contribution, which is sketched out here. And this Berry curvature can actually vary in a system with topological transition. So that means that this parameter here, this coefficient of proportionality, is not necessarily temperature dependent or not necessarily in constant. It can reverse in sign in some cases, for example. So that means to directly infer the sign of the magnitude and the sign of magnetization with anomalous Hall is challenging in some of these cases. And sometimes we need probes that can directly measure the magnetization. Okay, and this brings me sort of to the main topic of my talk, which is the challenge of working with these ultra-thin magnets. Normally most of these phases will have magnetization between 10 and 100 EMU per centimeter cubed. And if we look at like a very large sample, I mean, 0.5 centimeters is huge by the standards of these flakes, but it can sometimes be achieved. Okay, the raw moment is like 10 to the minus 7. Which is certainly out of reach for most standard sort of magnetometers like a VSM or even second generation squids. It really takes the latest generation squids, such as a vibrating squid VSM, to sort of attain these levels of sensitivity. And first of all, there are not that many of these things around. And second of all, when you're doing this kind of measurement, you have to be conscious of the fact that even a single microgram of dust, of hematite, or even of magnetite, Fe3O4, that's sufficient to give a magnetic signal that is, 2 orders of magnitude larger than the film that you're trying to measure, or the flake you're trying to measure. So it's both very challenging, but you are also having to be extremely clean to get good measurements. So we need probes and experimental techniques that can directly separate the background signal and the primary signal of these ultra-thin magnetic layers. And, there's a variety of techniques around that can do this. Of course, the best techniques probably to get started with are the lab-based techniques. But a lot of these techniques are limited in the sense that they image the dipolar fields, which tell you something about the magnetization. But often we want to know in absolute units, the magnetization and the domain distribution. And so these larger facility-based techniques, that synchrotrons, cyclotrons, and neutron sources, often allow unparalleled view into the magnetism of these ultra-thin layers. So, it's important to distinguish that some of these techniques really measure the magnetic dipole field, so they measure the stray fields coming from magnetic domains. But whereas other techniques like X-ray dichroism and polarized neutron reflectometry, these are actual measurements of the magnetization and can be converted to absolute units, which is sometimes useful. And of course, some of these techniques are also sensitive to antiferromagnetic order parameters, which is quite exciting. So I'm going to talk about now this technique that I've invested most of my time in developing, and the main one that I use is polarized neutron reflectometry. And I'll emphasize some of its unique advantages relative to the other techniques. Of course, it also has some disadvantages, which I'll mention in passing. So polarized neutron reflectometry is a beam-based technique, okay? And at ANSTO, we have a variety of tools for studying ultra-thin films. All of our instruments, which are rather large, they're almost the size of a house, are named after animals. So we have the PLATYPUS reflectometer, the SPATS reflectometer. We also have a variety of smaller equipment, ellipsometers, physical property measurement system, and also the ability to polarize helium-3 for mobile polarization measurements on all the diffraction instruments. So the tool that we use for polarized neutron reflectometry primarily at this point is PLATYPUS, okay? And PLATYPUS, this is a top-down view of the instrument, okay? And the basic premise is that we will bring a beam of neutrons in at very low angle. Typically, the angle of incidence is less than 1 or 2 degrees. And we will analyze the reflection of this beam of neutrons. And the neutron, of course, is a quantum particle. It is both a particle and a wave, so it can undergo wave interference and wave reflection. And this is essentially what we're measuring. Now, if we take a big substrate like silicon, okay, and we just measure it by itself, we'll observe a reflectivity that looks something like this. Essentially, we'll get reflected neutrons up to some critical angle that we'll get 100% of reflection, which means in this case 0, because it's a log scale, okay? And then as we go past the critical angle of reflection, our reflectivity will fall off according to Fresnel's law, approximately as 1 to the power of q to the 4. Okay, but now if we add a thin layer to the surface of our silicon substrate, we will observe quantum interference fringes, which we call kissing fringes, which tell us about the thickness of the layer and the chemical composition and scattering in that layer. I should say, if you're unfamiliar, we tend to plot things out in terms of this variable Q, and really this is just related to the angle of incidence, but it takes into account also the wavelength of the matter wave of the neutron wave here. And the reason we do this is because different reflectometers often use different wavelengths, but you can always convert reflectometries between each other to collapse them to look exactly the same if you plot them in terms of this variable, which is the scattering vector. Okay, so this is a more descriptive and to scale picture of the whole thing. Let's see if I can get it to play. All right, so the neutrons come from the main reactor and they travel down a long guide towards our instrument. And this guide is, tens of meters long, and it travels towards the platypus. And initially we have a continuous source of neutrons. So it's just a continuous beam, but we actually chop this up into pulses with these orange spinning mechanical disks, which are called choppers, to produce pulses of neutrons, which then irradiate our ultra-thin film and undergo reflection and are collected on an area detector some distance away from the sample. And so what we're interested here is the intensity of the neutron reflected beam as a function of angle on the sample. And so we obtain these interference fringes, which give us information about the chemical composition. So to sketch this out in terms of more mathematically, we can think of this as a generic problem of waves interacting in a stratified media. So we can describe the wave, in this case the neutron, by a plane wave with a K wave vector like this. And of course, this wave can do several things. It can first, it can be reflected from the primary surface of the film, and it can also be transmitted, or some portion of the wave may be transmitted, okay? And it could also even end up going into the substrate. So what we end up doing is writing the wave function in these three different regions, okay? And we can insert that into a one-dimensional Schrodinger's equation. And we impose the boundary conditions that both the wave function and the derivative of the wave functions need to be continuous at the boundary. And ultimately, this allows us to calculate the observable, which is the intensity of the reflective beam, or essentially this magnitude of this term here. Now, this formula I've given you, this treatment I've given here could be applied to anything. It could be applied to electrons or even atoms, or anything that's described by a wave equation or Schrodinger's equation. But what's unique for neutrons really is about what determines the scattering within each material, which is the potential in each of these layers. And this is where the unique contrast from neutrons arises. So the scattering potential in neutrons has these two main parts. So the neutron sees a one-dimensional quantum potential that contains a nuclear part and also a magnetic part. And what makes the neutron so sensitive to magnetism is actually these potentials are almost the same in magnitude often in most materials. So there's a very strong magnetic contribution. So when we look at this part, basically we have n, which is the number of atoms per meter cubed here. All right, we have the mass of the neutron, Planck's constant, and then we have an optical constant, which is the average neutron scattering length in a material. So this tells us that neutrons scatter differently from different elements. Oxygen and hydrogen have different B factors. And then finally, the neutron couples with its magnetic moment to the local B vector, which is primarily determined by M in practical situations. Okay, so if it's simpler, you can also think of this as a refractive index, and many people do. So convert this potential into an effective refractive index, and then the neutron behaves much like a light wave would in a birefringent material or crystal. It sees the spin up and spin down neutron see different refractive indexes. Okay, so just to deconstruct, both of these terms in more detail, many people use neutron reflectometry to study non-magnetic materials, in which case the second term just vanishes, right? And you might ask, well, why would you want to do that? And it has to do with the fact that this nuclear term by itself is very useful, and it's often useful particularly for very light elements. So when we do X-ray scattering or electron microscopy or whatever, we're relying usually on interaction between an electron or an X-ray with the electron density of an element. And this means, for example, that as we go to heavier elements, they always tend to dominate over lighter elements. But neutrons are different. They're interacting with nuclei by the nuclear force. And this means that neutrons have very different scattering lengths. And light elements like hydrogen or oxygen can be almost as heavy, strongly scattering as barium, for example. And that can bring out contrast or hidden features in situations where it's otherwise difficult to see oxidation, for example. And so biologists and chemists use this a lot. I just give a quick mention of this because I thought it was very topical. So the big advantage for neutron reflectometry for non-magnetic systems is when you're doing light elements like hydrogen or lipids or membranes. And a lot of polymer chemists and biologists do this. A recent study on the COVID spike protein used neutron reflectometry to look at how it interacted with a model cell membrane. And those measurements were actually done at ILL in France, but the samples, the deuterated samples, were prepared at ANSTO. So I think this is quite good work. But of course, for magnetic people, there's still advantages to being able to see light elements, particularly if we're looking at organic junctions. We had a brilliant talk about the fullerenes yesterday. And it's also generally true that these very thin metallic and magnetic layers tend to be vulnerable towards oxidation. So we often want to be able to detect magnetic dead layers or oxide layers in these systems. Okay, so talking about now the second term, where we can just deconstruct a little bit more how this magnetism introduces by the second term. So what essentially happens is that the spin-up neutron sees one potential where this magnetic term adds to it, and the spin-down neutron sees a different potential, so a different refractive index, okay? And what really matters, although it's the B vector that enters in here, it's the scattering occurs at interfaces, and the key factor is actually the differential of the potential, and which is entirely determined by M, because H is continuous, and that's the applied field, and that's continuous throughout the lab frame and in the sample itself, whereas M is not. So in practice, the key thing that determines the scattering or the strength of this potential is the magnetization of the sample itself, and the contrast and jumps in magnetization as a function of depth. And we can rewrite this potential in terms of this term, and we normally separate out the nuclear and magnetic term in this way. And the nuclear term I've already given to you. The magnetic term can be written in a number of different ways, but essentially the key thing here is that there's just a constant of proportionality that relates this either to EMU per centimeter cubed, or if you prefer SI units or some other unit, there's a variety of ways of converting, but this is essentially what we're sensing through this magnetic potential. It's a direct measure of the magnetization as a function of depth. So looking at what a pattern will look like in practice, this is an example of a polarized neutron reflectometry pattern, right? What we'll see is for incoming neutrons with spin up, which are here red, we'll see one reflection. And for incoming neutrons with spin down, which are here colored blue, we'll see a different reflection. And also at some angle, they will both be reflected with 100% probability. So this angle is the critical edge. It's determined by mostly the substrate in ultra-thin films. But what's really interesting for us, of course, is the splitting between the spin up and the spin down, which is the spinosymmetry. This tells us that we have a magnetic layer that's present, okay? And we see quantum interference fringes, and these fringes tell us about the thickness of the layers. And finally, the reflectometry would tend to fall off as a function of Q. This tells us about the roughness or the interfacial roughness of the layers. Finally, I should mention that in some cases, if you have a magnetization that is not co-aligned with the field, then the potential gets off-diagonal components, and you'll observe a spin flip signal, which can be used to measure the component of the magnetization that is at 90 degrees to the quantization axis or the applied field. So how is this done in practice? This is a picture of PLATYPUS. So here are these choppers I mentioned previously. We have a beam of neutrons that consist of both spin up and spin down. What we do is we polarize the beam at this point just after the choppers, so that only spin down are passed through. And so these are just illustrated that the spin down gets passed through, okay? And if we want the other spin channel, we can then, we have a spin flipper, which is basically an NMR type of principle of Mersey spin flipper, sorry, RF spin flipper. And this allows us then to select if we want the other spin channel, we can flip the neutron at this point. And so we basically, in practice, measure with one spin channel, then we activate the NMR spin flipper, and we measure with the other channel. Okay, and so the kind of information you can get from these measurements is the thickness, the deposition sequence, the roughness, the periodicity, etc. This is all very good. The thing is that some of these parameters can be measured just by looking at the splitting without really doing any modeling. Other parameters require some modeling. And the real question when we're trying to do this modeling, if we want to get an absolute unit for the magnetic moment or the magnetization, we need to try and reconstruct this potential, okay? And the ideal way to do this would be simply to Fourier transform the reflectometry pattern. Unfortunately, this isn't possible in general because phase information has been lost during the measurement. So, you know, what in practice we have to do is fit the experimental measurement, and sometimes there's an entire family of models that can fit the data almost equally well. And this is a well-known problem in the field. But this problem is more or less solved now. There's really some fantastic software out there, all open source. Here's a few different links that you might like to try. The one that we develop at ANSTO by my colleague Andy Nelson is RefNX. It's really capable of doing very complicated correlation plots and Monte Carlo sampling to explore different families of models and place bounds and find the local minima, and indeed the global minima in most cases. All right, the key thing, regardless of which software you use, is to try and constrain the variables. So this is an art form in itself. And I mean, often it's enough just to know roughly the thickness of the layer and roughly the composition, and that's enough to give a very well-constrained fit. But, you know, I like to do better in general. If we know this, we can generally know almost everything there is to know about this nuclear term in inorganic systems. We always know that most inorganic systems have about this many atoms per meter cubed. And we can calculate the average BZ if we know the average atomic composition. So what I like to do, for example, is use EDS mapping from cross-sectional TEM, where we know the atomic percentages of different elements. And from that, we can calculate B, in which case we have almost a fully constrained this first term. And I also like, particularly where we have very crystalline films, it's beautiful when we can see high resolution cross-sectional work, because then we can really construct atomic scale models of that interface, which bring a whole new level of certainty. So this is some work we've been doing on the garnets with Roshni Yadav. Okay, so there are many ways to pin down and constrain fits and to get very reliable fits in neutron reflectometry, and just using a few complementary techniques like X-ray reflectometry or Rutherford backscattering, normally it's possible to pin things down. And I should say, this technique works in amorphous and non-crystalline and complicated materials as well. It doesn't require crystallinity, although it can work for crystalline samples. For example, here's some amorphous titanium dioxide films, which we've implanted with cobalt, and we formed these very, very small crystalline cobalt nanoclusters inside, and we were able to resolve this with polarized neutron reflectometry. So it is possible to work on amorphous and nanocrystalline materials. So I hope I've convinced you that when it comes to the structural stuff, at least in inorganic systems, we can usually constrain this first term a lot. The question, of course, is how well can we know the second term, or what complementary techniques can we use to check that we have, double check that our answers are correct? And the answer is, well, there aren't really any techniques that are quite as accurate as polarized neutron reflectometry or as quantitative. So we do have a problem. Like, in a sense, we need to know in absolute units the depth of the magnetization in the sample. And, X-ray circular dichroism, resonant X-ray reflectometry, they're very helpful, but there's usually some level of uncertainty in the exact magnetic moment, 10, 20%, and there's some approximations in the model, for example, relating the sum rules to the actual magnetic moment. So these are very helpful. But the new technique that I've been developing to solve this problem is to really try and use theory to really construct structural models of the thin film bilayer or thin film layer and predict based purely on theory, which we can then use to double check the polarized neutron reflectometry fitting and vice versa. Okay, so this brings me to the final part of my talk, which is using DFT to model ultra-thin films and what we can learn from that. So density functional theory, is probably very familiar to most of you. It's kind of a very good approximation to the n-body quantum problem in solids. It also works in molecules and liquids. if we would write out the full n-body quantum problem, this is what the Hamiltonian would look like. We would have, terms for the interaction between the electrons, interactions between the ions, interactions between the ions and electrons. Clearly, there's a lot of terms, and even the classical problem here is impossible to solve, never mind the quantum problem. So DFT is really a set of approximations that allow us to approximate this in a useful way. It's not perfect, but it's very good. And it starts by using the Braun-Oppenheimer approximation to basically fix the position of the atomic cores or the ions, okay? And then approximate the electrons in terms of a kind of average functional, or you can kind of think of this as a cloud of electrons, where electrons interact more as a kind of gas with each other, rather than as individual electrons with individual coordinates. Okay, and this was shown to be very valid by the Cohen-Sharmak theorems. But of course, the payoff here is we need to approximate the exchange correlation, so the interaction between individual electrons that, for example, determine the Pauli exclusion principle. We have to build that in some way into the model, and this is done through the exchange functional. So we've been using this technique for a few years now. We use mostly VASP, which is the Vienna ab initio simulation package, but we started by simulating, just unit cells of magnetic systems. For example, these are iron platinum 3 systems that can be ferromagnetic or anti-ferromagnetic. And over time, though, we really wanted to build entire slab models of thin films. So over time, we've developed a technique to build the entire thin film. This really only works for very thin films with a few atoms in. It doesn't work for millions of atoms, but it basically starts by, we need some identification of the phases and the orientation. We then build from the crystal structure files the basic unit cells, and we cleave these unit cells along specific orientations and assemble a heterostructure using a variety of different bits of software packages, okay? And then we end up with something like this. And so why this is approximating a thin film is we have periodic boundary conditions in these directions. So we have an infinitely long film in these directions. So it's a cross section. We're looking at side on of the film. And then we break the periodic boundary conditions in this direction by introducing a vacuum slab, okay? And we also have been using other packages, including Quantum Espresso. Finally, we run a high-quality self-consistency cycle to get the magnetic depth profile out of such a thin film. And this is all really possible because of this very powerful computers that are coming online now. For example, I use the Gaudi supercomputer. What I really like about this computer is that it's illustrated with this beautiful art from a local artist, and the art symbolizes the bringing together of an even greater collective knowledge system. And these type of computers are allowing us to simulate, real thin film structures for the first time. So I'm conscious of the time. I'm just going to spend in the last 5 minutes giving a sort of tangible example of this. This is work that was led out of University of Western Australia by Mikhail Kostelev, and he was looking at ways to develop magnetic hydrogen sensors. So, hydrogen is an amazing fuel potentially for electric vehicles. The problem is it obviously can be explosive, and so one needs sensors that can address this problem. And palladium is an important component in all known hydrogen sensors because it has a high selectivity for absorbing hydrogen. The problem is that in all palladium-based sensors, there are some shortcomings. For example, electronic sensors are susceptible to arcing. Optical sensors can be complicated to set up, and mechanical sensors tend to age. So Mikhail asked the question, could we use an out-of-plane cobalt palladium thin film as a sensor and detect its magnetic signal as a function of hydrogen loading? And he developed a very clever FMR on-chip application that allows you to do ferromagnetic resonance. And indeed, as hydrogen is charged up into the system, the ferromagnetic resonance shifts. And this was implemented on our PNR beamline, and we simultaneously did polarized neutron reflectometry to watch as the system was charged up with hydrogen. And indeed, there are some subtle changes in the magnetization and also some subtle changes in the position of the quantum fringes that show that the thickness of the layers have changed, and there's some changes also in the magnetic depth profile. The changes are very subtle. Essentially, not much is changing in the magnetization. At most, there's just a small change in the interfacial regions. So just to show how DFT helps us in this case, we construct the slab model, we calculate the density, the spin density, and you can see these red highlighted regions show some spin density has crept across the interface from the cobalt onto the palladium. We can then extract the magnetic depth profile, and what we can find is that there's when we include the spin-onward interaction, the calculated value is very, very close to the experimental moment of cobalt, okay? And indeed, there's some small magnetization that's in approximately the right ballpark for the palladium. And then we can repeat the calculations. And what I can draw your attention to, once we add hydrogen to the model, there's swelling of the palladium layer in agreement with the experiment. There's also very little change to the magnetization, just a small or subtle variation around the interface. But the main thing that we also learn from these models is that the spin polarization at the Fermi level with hydrogen does get affected by the presence of hydrogen. And there's a drop of about 15% in the spin polarization, which explains or may help explain the damping of the FMR signal. So just, we want to make this method more quantitative in the future. And, the key thing here is after we have the DFT cycle, we can extract the charge density file, and we end up with a grid of values like this, which tell us the spin density at any position. And we might end up sometimes with antiferromagnetic structures like this. So we need to perform some averaging, which we do with some kind of Gaussian to approximate the averaging that occurs in the experiment, both laterally and vertically. Okay. All right. And in my last minute, I'll just mention that we've continued this project. We're now looking at really, really thin layers, and we're looking at replacing the cobalt with palladium. And this work has been led out of McDermott. And we're looking at how these systems, which are known to be spin gapless semiconductors, with systems which are parabolic but have zero gap in one spin channel, were recently also shown to have the topological Hall effect in very thin palladium bilayers. And we wanted to explore this and explore their magnetic structure. And so this is some ongoing work that I'm really excited about. It's certainly work in progress. So we've looked at very, very thin layers. You can see these layers are thin because we have only one quantum interference fringe out of very high Q, which means that roughly the layer is about one nanometer thick. And indeed, this layer is magnetic here. This manganese 2 cobalt, we find it's only about 1 nanometer thick. That's actually magnetic. Below it, it's a magnetic dead layer at the interface with magnesium oxide. And we're in the process of modeling that. The challenge here is that these films are polycrystalline, and we need to model different orientations. So certainly this is sort of at the limit of what's possible with DFT at the moment. And I would say DFT is not a panacea. It works well, but it's unsuitable for some things like large systems or finite temperature effects. So increasingly, we're looking to collaborate with other groups who do molecular dynamics, Metropolis, Monte Carlo, micromagnetics, to try and kind of come a unified approach. So I thank you very much for listening and staying with me. Just in conclusion, these ultra-thin magnets offer really interesting and useful physical effects. Polarized neutron reflectometry is one of the very few ways to quantify the magnetization in absolute units. And DFT is a natural complement to polarized neutron reflectometry for very thin films. And we're able to model these, with high performance computing. So hopefully this is an area where we'll see some growth in the coming years. So thank you very much. And I'd just like to acknowledge all the co-authors and collaborators who participated in this, and also thank the Australian Research Council for funding us, Fleet, and also the IEEE Magnetic Society who supported Grace during her work. So thank you very much. And in my last minute, I just want to mention if anything I've said is somewhat interesting to you, I should mention that the Australian Centre for Neutron Scattering at ANSTO is open to all users, and anyone in the international community can submit proposals. It's free, but it's based on a merit-based peer review process. The next deadline is 30th of September. And in addition to the PLATYPUS reflectometer, which I spoke about today, there's a variety of diffractometers, spectrometers, and other instruments which may be of interest. So if you'd like any support or guidance or a hint about which instrument might be of interest to you, please feel free to shoot me an email. Okay, thanks very much.
Thank you, David, for your very wonderful tutorial. And now the floor is open for questions. Any audience who wants to ask a question, please raise your hand.
Yeah, I have a very quick question. Thanks, Professor David, for this wonderful tutorial. And it is part of your second part where you have been explaining the measurement techniques for this neutron reflectometry. So you have been showing what are the things that can be measured using this, like edge roughness, and in-plane magnetization was one of the things. So it is like only restricted to in-plane magnetism measurement, or out of plane could also be explored using this technique? Because
Yeah, so that's a good point. Unfortunately, the nature of the scattering is that it only sees the in-plane magnetic moment. But we do sometimes work with out-of-plane systems. And the way we do that is we just apply a big in-plane magnetic field. and we magnetize them in plane. So we are capable of applying a few Tesla at the sample position, which is usually enough to magnetize things back in plane. So we do some work at out of plane systems, but yes, this is one of the challenges with the technique.
Oh, I see. Okay, thanks for that.
Okay. Any other questions? I have a quick question about your future work about implementing the temperature effect in DFT. So you mentioned about the Monte Carlo and some micromagnetics. So is there any specific plan of how to implement it? Because I heard of some DFT calculations can consider temperature effect in itself, not using the other techniques. So I wonder, what is your plan?
So DFT already can do a very good job in ab initio molecular dynamics of temperature effects in atomic position. So for example, I think I have a video of this, like we can simulate an amorphous interface, for example, at a finite temperature, and we can build the structural position very well, okay? But with the magnetic ground state, DFT is a 0 Kelvin theory. So it's stuck in the 0 Kelvin magnetic ground state. So we don't see proper thermal treatment of magnetic effects, not in normal DFT anyway, only in these, higher level theories. So what most people do is they'll combine DFT with Monte Carlo or micromagnetics, and we do this as well. So we extract from the DFT 0 Kelvin state, we extract the exchange interactions, for example, and the anisotropy if we're able to, and we feed these parameters into the next level of our model, which will generally be micromagnetics or Monte Carlo, where we have temperature built into them more rigorously. So we have done some of that work. The reason I didn't talk about it so much is that we haven't got a perfect pathway for doing that. We haven't got a standard way of doing that yet. Whereas at least with the DFT, it is standard. It is kind of standard now.
Okay, thanks. Any other questions?
David, if I can just ask a question, what are some of the sample constraints? So if I want to use use PLATYPUS or another neutron reflectometer, like sample size wise, or anything that I need to keep in mind as I make these samples?
That's an excellent question, Sam, and I probably should have mentioned that. So we want a reflective sample, and the more reflective, the better. So it should be almost like a little mirror flat piece of silicon is ideal, right? So we generally want samples that are at least 10 by 10 millimeters worth of reflection. We can work with slightly smaller materials. In some cases, we've done a few millimeters by a few millimeters, but the bigger is better because it speeds up the measurement, by orders of magnitude. So yeah, I would say generally as a guideline, 10 by 10 millimeter film, very low roughness, in the sense that it should be, the root mean squared roughness should be less than a few nanometers to get a nice signal. And in terms of thickness, funnily enough, we're better at looking at thin films, like 1 nanometer or 2 nanometers is easier to look at than something that's a micrometer thick. So our sweet spot is sort of between 4 nanometers and 100 nanometers in terms of film thickness. That's where it's easiest to do the experiments.
Thank you.
Okay, then let's thank the speaker again for the very nice talk. And I think this is the end of the conference. Hans, you can close the conference now.